In this video, I wanted to talk about friction on curved surfaces. So things like a belt and a pulley, that sort of problem is what would be classified as a curved surface. So in the PE handbook, there's a formula, which is F1 equals F2 times E to the mu theta. So here, F1 is the force being applied in the direction of impending motion. And then F2 is the force applied to resist impending motion. And then theta is the angle of contact of the belt or chain or rope or whatever. And that is going to be in radians. Make sure that you use radians for that. And then mu is coefficient of friction. So I have an example problem here. So we have this pulley right here, and we have a rope draped over it, and on one side we have a 100-pound load, and then we're pulling on it in the other direction. Our angle of contact is 80 degrees, and our coefficient of friction is 0.4. So we have two questions. The first one is to find the force F required to prevent slipping, and B is find the force F to raise the load. Right, so starting off, I'm just going to think about this intuitively. When we're finding the force required to prevent slipping, friction is actually helping us because friction is going to go in the same direction that we're going to want to pull in. So I'm going to assume that it's going to be less than 100 pounds. Whereas for the force to raise the load, friction is hurting us. So I'm going to assume it's going to be more than 100 pounds. That's just kind of a quick spot check on these answers. All right, so using this formula from up here, we get F1 equals F2 times E to the mu theta. So the hardest part about using this equation is making sure you pick the right F1 and right F2. So F1 is being applied in the direction of impending motion. So for A, when we're trying to find the force to prevent slipping, that's going to be the weight. And then our F2 is resisting the impending motion, so that's just going to be our F. So if we rearrange this equation, we can set F equal to F1, or the weight, over E mu theta. So that's just going to be 100 pounds divided by E to the 0.4 times 80 degrees, and then we're going to convert this to radians. So times 2 pi radians per 360 degrees. And that comes out to be 57.21 pounds, which, again, a good spot check. That is less than 100, which is what we would expect because friction is helping us. Also moving on to part B, I'm going to rewrite this equation here. So again, the trickiest part is making sure you pick the right F1 and F2. So in this case, the force being applied in the direction of impending motion is going to be F because we're trying to raise the load. Then the force resisting is going to be the weight. So we don't actually have to rearrange this at all. We can go right into this. So 100 pounds times E to the 0.4 times 80 degrees times 2 pi radians per 360 degrees. So our F is going to be 174.81 pounds, which again as a spot check is more than 100, which is exactly what we would have expected. So another type of problem you might see related to friction on curved surfaces is it'll give like a two pulley system, and you'll have a belt that goes around them. And the thing here, let's say it's spinning this way, and I'm trying to think off the top of my head what a good question would be. But the point I'm trying to make is about tension, related to the direction of tension. So if we just draw like a free body diagram, if it's spinning this way, clockwise, tension is going to be down here, and this part of the belt is going to be kind of slack. So you're not really going to have much force acting over there. So for your F1 and F2, your force, your F2, which is resisting impending motion, that's going to be your tension. If it's spinning, for a spinning, a spinning belt system. But yeah, I hope this helps.